going to rush through the introductions because both Deena and Glenn have been introduced before. They are giving a talk called The Documentation of the Artist Source Code as a Preservation Tool. Glenn Wharton and Deena Engel.
Well, we're going to play a little bit of a tag team here. I'm going to start and then hand it off to Deena, and then I'll come back at the end. I'd like to just start by suggesting that some of you might be feeling a little bit overwhelmed from all that we've been covering and learning, and especially from the workshops this morning. I'm going to come back to this state of being overwhelmed at the very end of this presentation. But to begin with, I was overwhelmed myself when I became the first time-based media conservator in the United States in a museum in 2005, in the largest media collection, I think, in the world, over 2,000 media artworks, and coming into this field from sculpture conservation. So you can imagine how overwhelmed I felt with this large and very important collection to take care of. I started by doing an inventory. There wasn't really a full inventory of all of the media objects at MoMA. The next step was to begin a risk assessment of categories of works of art, then launching some projects and bringing a lot of people in to help me, including eventually bringing in 2 employees to help me, Peter Alexic with deep knowledge in audio and visual technology, and Ben Fino-Radin with deep knowledge in software-based art, as we all know. We digitized a collection of over 1,500 analog audio and video works. We launched the digital preservation repository. And after getting some of these projects going, I identified the software-based works as the most vulnerable, highest risk in the collection. And in particular, those that were dependent on software or artist-generated source code. So that's just a little bit of background. I linked with Deena Engel, professor of computer science at NYU, to help me with this, or to help MoMA with this. She performed 3 technical risk assessments of software-based works that we selected. And then I went on to perform another 11 assessments, often working with MEAP students. We conducted interviews with a number of artists and started building the kind of documentation we needed. The next level was to think, well, what are the highest vulnerabilities among the works that are dependent on artist-generated source code? Working with Deena, we decided it was the source code itself and keeping it operable in the future, the needs to recompile or the needs to work with it one way or the other. And it was Deena that suggested documenting the source code. So she will tell you about the work that we did with her students, her computer science undergraduate students at NYU, on 3 different artworks. I just want to very quickly introduce these 3 works. This first one is, wish I had the time to actually go on the artist's website. You should go on the artist's website because it's really fun to play it. It's called Thinking Machine 4, and it's by Martin Wattenberg and Marek Walczak, who are both programmers. Thinking Machine 4 is a chess game that you can play with, play on their website. And it's written on Java. And what happens is once you make a move, then all of these curved lines come out and overlay over the chessboard as the computer is deciding what are all of the options for moving all of the pieces on the chessboard. And the ones with the thickest lines or the brightest lines in the ends, it's what determines which move is going to be made. The next work by Rafael Lozano Hemmer is called 33 Questions Per Minute. I'm sorry, it's not. It's Shadow Monsters by Phil Worthington, 2004. This work is written in processing, which we all know, processing 7, which works in an environment that uses Java. And for this work, it's interactive, so the public actually makes what look like shadows on the screen, but they're actually computer generated, and they're in the form of monsters that make noise, and it's really a fun piece. It's been installed several times now at MoMA. The third one is 33 Questions per Minute by Rafael Lozano-Himmer, 2000. It consists of 21 small LCD screens. It's a text-based work that generates questions in several different languages, supposedly randomly, at a rate of 33 per minute, which is, he says, is the sort of the threshold for human understanding, or the ability to read questions on these screens. And it was actually written in Delphi, which is a derivative of Pascal. And one of the interesting things about this is that the students were unfamiliar with the language, so they actually had to learn the language in order to perform their documentation research. So that's my quick rush job through to introduce you to the 3 works. Deena is now going to go more deeply and talk about the work that we did on each work.
So think back to this morning when we were in processing, and I talked about annotating code, both to make it understandable, and also we used the double slash to remove a background at one point, which I would at that point consider unused code because we weren't using those lines of code. Software maintenance is a standard field in software engineering, and as in general in software engineering, it's required whenever there are changes to the operating system, whether there are updates to the languages, changes to the hardware, or changes to relevant multimedia formats. And I think the context of how we approach this at MoMA is analogous to what I've seen when I've visited conservation labs, and there may be a handful of paintings that are getting very special treatment. They're being imaged very special ways. They're getting x-rayed. Conservation scientists might be taking tiny bits of paint from the canvas in order to do a chemical analysis. So not every painting in the museum is going to get that level of treatment. But the paintings in the museum that merit that level of treatment for whatever reason, whether because they are seminal works, whether because they are greatly at risk, those are, these works that I'm going to talk about are in that category, that they are seminal works to the collection, and they are works which do not fit into easy categories to be grouped with others. In general, in software engineering, there are several approaches because documenting source code is a standard operation in software engineering. We annotate code, as you saw this morning. There may be narratives, which are natural language descriptions, visuals, and we'll take a quick look at UML diagrams. We've talked about comments this morning and annotations in the code which tell us both if the artist's comments are available. That's not the case if we've had to decompile a compiled artwork, but the comments will also show us unused code. Narratives can be very useful, particularly for conservators who may not be able to read the code, because reading code, by the way, is, for somebody who knows the programming language, would be like reading English, or for a musician to pick up a score and to be able to read a musical score. Reading code, this morning, in fact, I was enjoying looking at a lot of your code because I could visualize what was going to happen, which is why a lot of times when somebody asked what was going to happen, I said, oh, you need to run it, because I'm not going to tell you. But I look at source code the way I look at a musical score, which is I hear it, when I look at a musical score, I hear it in my head. So the narratives are a way to say, this is what is happening in so-called in plain English. Whether the narrative is for a small block of code, such in this case from Shadow Monsters about how the sounds are selected, whether it's for a larger block of code consisting of multiple functions. Visuals can be very useful. This is the program flowchart from 33 questions per minute. Because it was in a language that most people are no longer familiar with, it was very useful to have a program flowchart, to be able to identify how the programs were called, because the way that they were actually stored in the text files did not match how they were actually being called because of the nature of this language. UML, the Unified Modeling Language, is another approach. Thinking Machine was in processing. The complete UML diagram of all of the functions at a human-readable scale was probably wider than I can show. We had a great deal of difficulty displaying it when we presented it to the museum. This is another method that is widely recognized in the software world and in the business world for diagramming and identifying, creating visuals for software. So I'd just like to talk a little bit about where the areas of software documentation vary from traditional software engineering methods, such as if you were documenting the source code to an ATM machine, versus what we need in the art world. Some of the decisions that are made are very clear when you start to document and look at the source code. 33 questions per minute, for example, can run in English, German, or Spanish. This language selection actually happens in the configuration file, in the code itself. What that means is that the artist could ship one executable or one set of files to any museum in the world, and whoever installed it had instructions to set that flag for the language. But it's one program. We also found situations where the source code revealed operating system specific artifacts. So for example, you saw, in the picture you saw of Shadow Monsters, there were only 2 people playing with the work. But you could imagine that if there was a class of kindergartners in the room, that piece would crash pretty quickly. And in fact, what happens is it restarts, it reboots the machine and restarts, but it is programmed in such a way on the operating system level as to facilitate that, so it's not quite transparent to the user, but very close. One of the biggest issues in terms of preserving software art is, and any software, are the dependencies on special libraries. So Shadow Monsters, we found, depended on a series of special libraries, one to play the sound files, one was a physics library. A physics library is code to make things look like it's bouncing, things like that. Those special libraries were no longer available when we were doing the source code analysis. Had that been known sooner, we might have had the opportunity to obtain that source code. Last but not least is custom hardware. With works of art, although it hasn't been emphasized in this conference, many of the works that we're discussing, and in this particular case, 33 questions per minute, actually required custom hardware. So not just like Shadow Monsters, in which part of the work is operating on the operating system level, but actual custom hardware, in which case the software is specifically written to drive the custom hardware. In terms of the source code, we also wanted to understand what's happening in these works and the aesthetic aspects of the work that need to be documented. This deviates from standard procedures in software engineering because with an ATM machine, it is what it is. We're not too worried about what it looks like. We also wanted to look at the artist's process. Color space and color considerations are very important. This morning we introduced the concept many of you are familiar with, but how to actually define colors in RGB, in the color space red, green, and blue. There are other works that are conceived of by the artist, for example, and defined in HSB, which is hue, saturation, and brightness. So if, for example, you want to mathematically work with the colors, with the numbers that determine the colors, and what you're looking at is complementary colors, yellows and purples, or reds and greens, blues and oranges, and so forth, you probably would be better to be working in an environment in which you're creating and defining your colors in the paradigm using hue, saturation, and brightness, because mathematically the numbers will work out more easily. You can build your algorithms, even if you ultimately display them in an RGB format. So the color space and the color considerations are very important, and this can only be gleaned from the source code. I don't think we can tell just from looking at a work of software art how the color was conceived by the artist. Speed of execution is very important. One of the things we found in Shadow Monsters is that the artist used a very unconventional way to program delays into the software where he wanted the motion to slow down. Because we were able to identify where those delays were, we were able to predict what would happen if this piece were simply played on a newer machine, which is that those delays would have disappeared. Some programming techniques allow you to actually measure delays by seconds or fractions of a second, but other techniques will be impacted by changes in hardware. Very important to know that with a work of art. Randomization plays a very important role in how an artwork behaves. In some cases, for example in Shadow Monsters, the sounds that are selected appear to be random, but in fact, they are played in a very specific order and selected in a very certain way. So if you were to make a very small mouth like this, it would probably be one of the higher pitched sounds, but in fact, they are picked in a specific order. The words and the phrases in 33 questions per minute are randomly selected, and what you get are sentences that are meaningless, but the software works very carefully with lists of words in similar categories, so lists of nouns or lists of verbs. And because it's available in English, Spanish, and German, which have different sentence structures, then the lists are organized in such a way so that a past participle in German will appear at the end, whereas in English, it would appear closer to the verb. So in this way, it is grammatically coherent, but it is randomized behind the scenes. The chess game, on the other hand, in Thinking Machine, if I may give this away, to everyone's surprise when we presented our results, and that may be disappointment, it's entirely scripted. There's actually no randomization. It's entirely scripted, and the game will play the same as often as you wish to play it. Another issue from a conservation perspective that can be very difficult to determine by eye without examining the code is the source of the images. So, for example, in Shadow Monsters, there's a series of PNG files to represent hives on the skin and funky teeth and all of this. But in Thinking Machine, all of the chess pieces are dynamically drawn as the piece runs. So what this means is that as you're working with the piece or conserving with the piece, for Thinking Machine, there are no external image files to worry about. On the other hand, the software, if there are any variations in the software, can have a dramatic impact on how the images actually look.
Okay, to conclude, I have some points I'd like to make. First of all, the aim of this project was to perform some initial research to investigate the potential for using documentation strategies from the software engineering field for maintaining commercial software, apply it to works of art in museums to see if it would work. And I think we concluded that it did. In some cases, we felt it needed to be adapted, or that some types of documentation are probably better than others for certain kinds of work. We published the results of our study in 2 different articles, one in Studies in Conservation, one in the Journal of the American Institute for Conservation, for those who are interested. But there was a big surprise along the way, and that was that we discovered, as Deena has pointed out, a lot of aesthetic information in the code, including a number of trials and errors and unused code that the artist didn't delete. So it's still sitting there. So in the second article, we titled it Source Code Documentation as Technical Art History. So this was a discovery that actually, in addition to serving for the preservation of these works, this kind of documentation, this kind of investigation in the code itself can tell us a lot about the aesthetic concerns, the aesthetic intentions, and indeed the actual working properties or working methods of the artists or the programmers that they used. So I think that there's a whole new area of research, just as in, say, a traditional painting, you can perform an X-ray, do infrared, ultraviolet analysis, cross-section analysis to understand how the artwork was made. We can do code analysis to understand how these works were made. So one of the themes that's emerged in this conference has been how much documentation we should be acquiring and how much documentation we should be generating in the conservation of software-based works of art. Well, we're now adding another reason to acquire and document these things for understanding artists' working methods and aesthetics. So that's just another argument for not only getting the code from the artist, even if you have an executable file, trying to get the code if you possibly can for preservation reasons, but also for research reasons. And I said I would get back to this feeling of being overwhelmed. You know, we've said before that not everybody can know everything. And I think that some of you, hopefully some of the younger people in the audience today, will be able to master all of the skills and the knowledge that we've been introducing over the last couple of days. And some of you won't. But I think the biggest takeaway is to work collaboratively and to find people in your environment that you can work with, including experts in various fields and programmers. But in this case, the liaison that we created between the museum and the university was a real win-win relationship. It was helpful for us, of course, to get labor that we didn't pay for, I might add. But it came at a cost, because it was our responsibility to work with Deena and her students as educators. So we very seriously took that on. So I think, you know, a museum can develop a good relationship, say, with a computer science department or professor at a local university, as long as they're willing to provide what they need to provide for the educational experience. And of course, for the students, they get the opportunity to examine the source code of important works of art, which has got to be fun, if not educational. So I think, you know, these relationships can be developed that can be very fruitful. So I would just like to put that plug in at the very end for the need to work with other people with deeper expertise and the possibility of university museum joint projects. So with that, I think we have a few minutes for questions. Wow.
Oh, no questions.
My name is Adriana Torres. I have no affiliations. I'm a pre-program student. I was maybe going to say this for the panel, but you did mention students as collaborators and the next generation of conservators. So, you know, I do feel very overwhelmed and like, where should I throw my focus? Now I'm feeling like, should I go back for computer science rather than conservation? Like, how do we blend all these fields, and where do I put my energies? Where would that best be used?
I'll take a stab at that. A parallel is when I started out as a sculpture conservator, I was overwhelmed with all of the art technologies that I felt that I should learn, and I actually had a whole lot of fun in my pre-program years and in my post-program years taking courses in jewelry making and silversmithing and bronze casting and learning the technologies that the artists use to fabricate these works that I'm now conserving. And were I a little younger right now, I would love to be taking courses in programming and learning how to create works of art digitally with all of these different formats. I don't think you need a degree in each one of these areas. I think there's plenty of opportunities now online and evening courses and to learn these tools. So I would advise anyone thinking of going into the field of media conservation to make it their business to learn the technologies as they go along. In order to get into the programs, I think the professors will be really impressed that you have this knowledge, but also just to help you implement skills as you move into the profession.
So I'd like to
Oh, yeah, you want to add something?
So I'd also like to add, so our wonderful teaching assistants this morning and some of our student speakers yesterday have had the benefit of learning so much from Joanna Phillips and Brian Castriotta here at the Guggenheim Museum. I think these are really fine opportunities. And in addition, I do hope that in the long run, that there will be academic programs for conservators, not just for paintings and not just for sculptures, but also for time-based media and software art.
There are 4 such programs in Europe, and there's talk about creating one in the United States. And of course, the Moving Image Archiving and Preservation program is a really good route as well to getting into media conservation.
Hi, I'm Ryan Langell, the lead developer at the Corning Museum of Glass, and I was wondering, you mentioned the color space modifications, RGB, HSB. I was wondering if you've taken that any further and gone to the point of getting ICC profiles for the displays that the works were designed to be represented on?
The works that we studied for this particular study were not very specific exactly how the works should be displayed, but the artifact we ran into this morning was an excellent example. When I was teaching processing and I did an example in what you saw were horizontal lines in blue that were variegated in a regular pattern, what I was seeing was exactly the same blue line repeated across. Those specifics are outside of my field. But I do believe that there does need to be a fair amount of, of course, research and attention to that. What's interesting to me, looking at the code and thinking about it from a technical perspective, is it helps me to get sort of into the artist's head. So we worked on a piece here at the Guggenheim in the last year in which the artist was so clearly working in HSB because he was very much thinking about the complementarity of different types of colors and adjusting colors, and he was randomly adjusting colors but within very specified ways. And because HSB is practically, it's like having a color wheel, and all you have to do is just sort of zoom across the wheel and you have the complement. Mathematically, that's very easy to do when you're in HSB, and then the conversion to present it in RGB is very straightforward. Whereas when I see artists working in the RGB space, such as Thinking Machine, you could see that the lines in green, for example, I don't know if we can bring the slide back, but the lines in green were in a fairly contained area, and the lines in yellow were in a fairly contained area. The colors are being randomly selected within a narrow range, but the range of the selection is much narrower than works that I've seen that have been conceived of in HSB. So I was thinking of it also as, how is the artist seeing? What does the artist see before he or she creates the work? Just as, what am I seeing before I put the brush in the watercolor and put it to paper?